Good morning, everyone. In today's session, we will discuss about the nuclear charge, the effective nuclear charge, the screening effect, penetration power, and the rules which are used to determine the effective nuclear charge, means the Slater's rule. So we will discuss about all these in today's session. Let's start today's session. First of all, we will discuss about the screening effect, or you can say the shielding effect. What do you mean by the term screening effect? Screening effect means the number, if there are the number of shells, then the attraction between the nucleus and the valence shell electron or any one of the intermediate electron is same or the different one. Means the attraction between the nucleus and all these electrons is not the same. The attraction between the nucleus and these first s electrons is more as compared to these 2s and the 2p electrons. Why that occurs? It happens because the attraction between the 2p electrons and the nucleus is less due to the presence of these intervening electrons. These intervening electrons act as a screen, act as a barrier, which decreases the force of interaction, which decreases the interaction between the nucleus and the valence shell electron. So that effect in which these inner shell electrons in the multi-electron atom act as the screen between the nucleus and the valence electrons, called as the screening effect, or you can say the shielding effect, right? Now, what are the factors which affect the screening effect? First factor is the nature of the orbitals. Which type of orbitals are present? Which type of orbitals act as a screen between the nucleus and the valence shell? So, depending upon the nature of the orbital, the screening may differ. For example, in case of s, p, d, and the f orbitals, the screening power of all these orbitals is not the same. The screening power of s is greater than p is greater than d is greater than f. Why that much difference in between the screening power of these s, p, d, and the f orbitals? As the s orbital is present more near to the nucleus as compared to the p, d, and f, so the screening power of s is greater than p is greater than d is greater than f. The next factor which affects the screening effect, that is the shape or the orientation of the orbitals. As all the orbitals don't have the same shape or the same orientation, so the orbitals having the different shape will cause the different screening to the different extent. For example, in case of the d orbital, you can see the d subshell have 5 orbitals: the dxy, dxz, dyz. In all the three, the shape is double dumbbell, but the orientation is different. In the dxy, these two dumbbells are present in between the x and y axis, while in case of the dxz, these two dumbbells are present between the x and the z axis, while in case of the dyz, these two dumbbells are present between the y and the z axis. So they differ in the orientation. All the three have the same shape, but they have the different orientation. As they have the different orientation, so they will have the different screening effect. Further, the next d orbital is dx square minus y square. Their shape is also the double dumbbell, but these two dumbbells are present on the x and y axis. On the x and y axis, as we compare dxy and the dx square, both have the two dumbbells, but in case of dxy, these two dumbbells are present in between the x and y axis, while in case of the dx square minus y square, these two dumbbells are present on the x and the y axis. So that's the difference. Next one is the dz square. In case of the dz square, there is one dumbbell that is present along the z axis and a spherical orbital that is present at the center. So that is a mixture of these two. One is like that of the pz and other one is like that of the s. So that is a dz square is a mixture of these two, pz and the s. So that is a dz square. So all the 5 orbitals differs from each other in one or the another way. So the different orbitals having the different shape or the different orientation will have the different screening effect to the different extent. So that factor also affects the screening effect. Next, as we can see, all the three p orbitals are of same shape. Px, Py, and the Pz all have the same shape, but they have nearly the same screening effect. They have nearly the same screening effect. These dumbbell are present on the different axis. In Px, that dumbbell is present on the x-axis. In Py, the dumbbell is present on the y-axis, and in the Pz, the dumbbell is present on the z-axis. So all the three p orbitals have the same shape, so they cause nearly the same screening effect. Next one is the number of intervening shells. Means as the number of the intervening shell between the nucleus and the valence shell increases, the screening effect will also be increases. As we move down the group, you can see in case of the lithium, you can see there is only one intervening shell, 1s2, 2s1. Means in between the nucleus and that valence 2s subshell, there is only one intervening shell, that is the 1s. But on moving down the group, the number of shell increases. On moving down the group, for example, in group number 1, lithium to sodium, potassium, rubidium, and the cesium, on moving down that, the number of intervening shells increases. In between the nucleus and the valence shell, the number of intervening shell increases. As the number of intervening shell increases between the nucleus and the valence shell, the screening effect increases. So that's the next factor which affects the screening effect, which affects the attraction between the nucleus and the valence shell electron. So the number of intervening shell increases. So the screening effect also increases there. It is to be noted that the electron present in the same subshell do not screen each other in general, but when we study about the Slater's rule, then we will see the electron present in the even in the same subshell will also cause something screening effect on each other that can be explained using the Slater's rule. But in general, while discussing the basic reasoning type question, we ignore that fact. The electrons present in the same subshell causes something screening effect with each other. That thing is generally been neglected during the reasoning type question. But in actual, we will see through the Slater's rules that the electrons present even in the same subshell may cause something screening effect to more or less extent. Next example, on moving left to right in the periodic table, what you will see, you will observe that on moving left to right, for example, from group number 13 to 18, in case of boron, you can see the configuration is 1s2, 2s2, 2p1, atomic number 5, boron. So that is the configuration. That's the diagram here for the boron. But on moving left to right in the periodic table, means as we move from boron to boron atomic number 5 to carbon atomic number 6, nitrogen atomic number 7, oxygen 8, chlorine 9, and the neon, like last one. So we are just showing here the first one, that is the boron of the second period element of group number 13, followed by the group number 18 element, that is a neon in the same period. You can see the electrons goes on entering in the same subshell. Means on moving left to right, the number of intervening shell between the nucleus and the valence shell remains same. Number of intervening shell remains same. Okay, so the screening effect will almost remains the same. So where the screening effect changes, the screening effect changes on moving down the group, because the number of intervening shell increases. But on moving from left to right, the number of intervening shell remains the same between the nucleus and the valence shell. So the screening effect almost remains the same. So that is the fact here. It is to be noted that the electron present in the same subshell do not screen each other, as I already told you, but through Slater's rule, that occurs some change in that particular statement. Means the electron present in the same subshell may screen to each other to some more extent, to less or more extent. Okay, so effect of the screening effect on the nuclear charge. Now the next topic is, what is the effect of screening effect on the nuclear charge? Means first of all, we must have the knowledge about the nuclear charge. Nuclear charge means the positive charge which is present in the nucleus, that is the nuclear charge. the positive charge, yeah, or you can say that the total number of protons present in the nucleus that creates the nuclear charge. Because the charge in the nucleus, the two main subatomic particles are the protons and the neutrons. Neutrons are the neutral one, so the charge, that is the positive charge, that present only on the protons. So the total positive charge is only due to the protons. So that charge that is due to the protons. So what is the number of protons? That will be the total positive charge, and that called the nuclear charge. So the total positive charge present in the nucleus due to the protons is called as the nuclear charge, and that is equal to the atomic number generally. So for example, in case of the lithium, the atomic number is 3. So the nuclear charge is plus 3. Nuclear charge is plus 3. So whether that charge, that is the plus 3, is experienced equally by all these electrons, means that these first shell, that is the 1s electrons, experience that charge as the plus 3 in case of the lithium, because atomic number of lithium is 3. So they are experienced plus 3 charge. So what will be the experience by these 2s electrons? These two electrons experience somewhat less nuclear charge, means that charge which is experienced by any of the electrons, that called effective nuclear charge. So that's the difference between the term that is the nuclear charge and the effective nuclear charge. Nuclear charge means the total positive charge, means the atomic number. Okay, so for example, atomic number of lithium is plus 3. That's the nuclear charge, but that charge is not equally being experienced by all the electrons. Okay, so the total positive charge experienced by any of the electron present in any of the shell of the given atom is called the effective nuclear charge. So the screening effect, what is the effect of screening effect on the nuclear charge? Means nuclear charge remains same, but effective nuclear charge changes on moving away from the nucleus. So why that mean happens? Due to the screening of these inner shell electron, these inner shell electron act as the screen between the nucleus, and the valence electron. Okay, so due to the screening by inner shells electron in between the outer shell electron, that the valence shell electrons, and the nucleus, what will happen? The attraction between the nucleus and the valence shell, the nucleus and the valence shell electron decreases. Because why that decreases? Because the nuclear charge felt by the valence electron is less than the actual charge. Then the bolo kya? Actual nuclear charge. Actual nuclear charge is somewhat different. But the effective nuclear charge, the nuclear charge that is felt by these valence electrons, is somewhat less. Why somewhat less? Due to the steric hindrance, due to the screening effect caused by these intervening electrons. Now the term is the effective nuclear charge. What is effective nuclear charge? The actual charge felt by any of the electron of any of the subshell of the given atom is called as the effective nuclear charge. Right? In case of the lithium, here is the diagram of the lithium. The charge experienced by 1s electron is somewhat different. The nuclear charge experienced by 2s electron is somewhat different. Means the nuclear charge experienced by these all electron is not the same. So what the nuclear charge experienced by any of the electron is called their effective nuclear charge. The size, as we all know, when we discuss in the next lecture about the size, that size depend upon the resultant of two factors. One is the screening effect, other one is that effective nuclear charge. When we discuss, we will explain what is the order of size on moving down the group, what is the order of size on moving left to right in the periodic table. So during the explanation of the size on moving down the group and on moving left to right, we will consider these two factors. We will consider the resultant of these two factors, and these two main factors are the screening effect and the effective nuclear charge. So by using these two factors, we can explain the interaction between the nucleus and the valence electron, because the decrease or increase of size depend upon the attraction between the nucleus and the valence electron. If the attraction between the nucleus and valence electron increases, means size decreases. If the attraction between the nucleus and valence electron decreases, the size will increase. So the increase or decrease of size that will depend upon the resultant of these two factors. Okay, when the attraction between nucleus and valence electron increase, and when the attraction between nucleus and valence electron will decrease. So the first condition is if screening effect is greater than effective nuclear charge, means if screening effect dominates over the effective nuclear charge. Screening effect means the screening due to the steric hindrance due to these intervening electron. If that is greater than the charge, the effective nuclear charge, which is being experienced by that electron, then what will happen? The attraction between the nucleus and valence shell electron decreases. As we can see on moving down the group, for example, in group number 1, the lithium, last one is the cesium. On moving down the group, the electrons are added in the next succeeding shell. So the number of intervening shell goes on increasing on moving down the group. So on moving down the group, as the electrons are added in the next succeeding shell, so the number of intervening shells increases. So number of intervening shell increase means screening effect increases, and the screening effect increases to such a large extent that it dominates over the increased effective nuclear charge. So that is the way here on moving down the group. So on moving down the group, what we'll observe? We observe that first condition means the screening effect dominates over the effective nuclear charge, and due to that the attraction between the nucleus and valence electron decreases, and as the attraction decreases, the size will increase. The size will increase. The next condition is if the screening effect is less than effective nuclear charge, means effective nuclear charge dominates over the screening effect. Where that will happen? That happens on moving left to right in the periodic table, as we already explained. About that, on moving left to right, for example, in case of the boron 1s2 2s2 2p1, the last electron enters into the 2p, in the 2p, that is the last electron. Intervening shells are 1s and the 2s, these are the intervening shell. On moving from boron to carbon, you can see the electron now entering into the same 2b subshell, means the number of intervening shell remains same, screening effect remains same. On further moving, in case of the nitrogen from boron to carbon to nitrogen, the electron enters into the same 2p subshell, so the number of intervening shell remains the same. On moving further, that is on from atomic number 5 to 6 to 7 to 8, that is of oxygen, the electron further enter into the same 2p subshell, so number of intervening shell remains the same. And same is the case with the fluorine, where the last electron enters into the 2p subshell, means number of intervening shell remain the same. So what we can see here? We can see here the on moving left to right in the periodic table in the same period. What we are saying here, in the same period on moving left to right in the periodic table, the electron enters into the same subshell, means the screening effect remains same. But you can see here the positive charge, that is the atomic number increases, means atomic number boron 5 to carbon 6 and so on, means positive charge increases, effective nuclear charge increases, but screening effect almost remains same. So means the nuclear charge increases, effective nuclear charge increases, so the effective nuclear charge dominates over the screening effect. So means what is going on moving left to right in the periodic table, as the electrons are added in the same subshell, so the number of intervening shell remains same, means screening effect remains same, and thus the effective nuclear charge dominates over the screening effect, and thus the attraction between the nucleus and valence electron increases, and because of that reason size decreases. So in that way we can explain about the increase or the decrease of the size. So the increase or decrease of the size depends upon the resultant of these two factors, that is the screening effect and the effective nuclear charge. We will also consider these factors during the discussion of the increase or the decrease of size along the period or down the group. Now the main topic here is the Slater's rule. The rules which are used to calculation of the effective nuclear charge experienced by an electron of an atom of an element are called as the Slater's rule. It is called as the Slater's rule. So how can we mathematically determine these Slater's, the effective nuclear charge? The effective nuclear charge is equal to the nuclear charge minus screening constant. Screening constant means how much screening is been caused by these intervening electrons. So minus that factor from the actual nuclear charge, the remaining one is called as the effective nuclear charge, right? So how can we calculate that effective nuclear charge using this Slater's rule? So there are some basic points behind that Slater's rule. That screening constant is shown by that sigma here. So the screening constant is determined by using the Slater's rule in by following these basic points. The first point is write, first of all, write the electronic configuration of any of the given element, 1s2, 2s2, like that, write them. After writing the electronic configuration, you have to divide all these subshell in some particular groups. So what these groups are, you will kept S and P together of a particular shell. For example, in the first shell there is only S, that is one group. In the second shell there are only S and P, so kept these S and P in the same group. So 2S and 2P form the one group. Next, in the third shell there are the three subshell S, P and D, but only kept the S and P in the same group. So 3S and 3P form the one group, and 3D is the next group. Okay. In the fourth shell, you all know there are the four subshell S, P, D, and the F. So S and P always be kept together in the same group. So 4S and 4P form the one group, 4D separate group, 4F separate group. In case of the 5S and in the fifth shell, 5S, 5P, 5D, 5F, 5G, and like that. So 5S and 5P in the same group, 5D in the separate group, and 5F is also in the separate group, like that. So that's the first point about the Slater's rule. First of all, write down the configuration and then write these subshell in a particular groups in such a way that in a particular shell, the S and P forms the one group, D from the separate group, the F from the separate group. Okay. Now the next, the example for that, for hydrogen atom, the grouping will be like that, because in case of the hydrogen, the atomic number is 1. So the configuration is 1s1. So there is only one group, that is 1s1. For example, in case of the helium atom, the configuration is 1s2. So there is only one group. In case of the lithium, the configuration is 1s2, 2s1, 2p0. Right here, 1s2. Correct it, 1s2 right here. So 1s2, 2s1, 2p0, we have now the two group for one particular shell. That for the first shell, separate group. For the second shell, S and P kept together, so the second group. Okay. Next, sodium. For the sodium, the configuration is 1s2, 2s2, 2p6, 3s1. For the first, in the first shell, there is only 1s, so the first group. In the second shell, there is 2s and 2p, that's the next group. In the third shell, there is only 3s1, there is no electron in the 3p, so that's the next group. Okay. Next, sulfur. Atomic number 16. Configuration is 1s2, 2s2, 2p6, 3s2, 3p4. For the first shell, in the first shell, there is only 1s, so the one group. In the second shell, there are only s and p, so s and p always be kept together, so that's the second group of 2s and 2p. In the third shell, the configuration completes only up to 3p4, so the electrons are present only in s and p, so that's the next group, that is the 3s2, 3p4 from the next group, and there is no electron further. So that's that about the grouping, how the grouping takes place according to the by following the Slater's rule. Okay. In case of the zinc, whose atomic number is 30, configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s2. So that's the configuration. Now how the grouping takes place. In the first shell there is only S, so the first group. In the second shell there are 2s and 2p. As according to the Slater's rule, these S and P are kept together of the same shell. The S and P are kept together, so 2s and 2p form the next group. Similarly, in case of the third shell, there are 3s, 3p and 3d, but in a particular shell, the S and P form one group, one group, while the D form separate group. So 3s and 3p form the one group and 3d form the separate group. Next, the fourth shell, there is only 4s according to the configuration, so 4s forms the next group. Okay, so in that way we can make the grouping. After the grouping, the second rule, the second Slater's rule is for any of the electron that applied on the same, only the electrons which are present in the same group. For any electron in the same group and the inner group electrons act as the screen, the outer group electrons has zero screening effect. For example, We write here the configuration of the zinc atom. The question may be asked in different ways. For example, for the zinc atom, the examiner may ask the question, what is the effective nuclear charge experienced by 1s electron? What is the effective nuclear charge experienced by 2s electron in zinc atom? What is the effective nuclear charge experienced by 2p in zinc atom? What is the effective nuclear charge experienced by 3s in zinc atom? What is the effective nuclear charge experienced by 3p in the zinc atom? What is the effective nuclear charge experienced by that 3d electron in the zinc atom? What is the effective nuclear charge experienced by the 4s electron in the zinc atom? So the question may be asked about any of the electron in any of the atom. For example, in zinc atom, the question may be asked like that. Okay, so the main point is the point number second. What it states that the electrons which, for example, the question is what is the effective nuclear charge experienced by 4s electron? So there is no electron after that. After 4s, there is no electron in 4p and so on. So the all electron will act as the screen, will create something screening constant. Fine. If the question is asked like that, what is the effective nuclear charge experienced by these 3d electrons? As the 4s are present outside the 3d, so there is no effect of these 4s electron on that 3d, means no screening effect by 4s, because they are not present between the, because here is the nucleus, after that first shell, first s, 2s, 2p, 3s, 3p, 3d. So means what is present between the nucleus and that particular electron for which we want to calculate the effective nuclear charge. We will see only these electrons. We will see only those shell or the subshell or the orbitals which are present between the nucleus and that particular electron. Okay. For example, as I am asking you the question, what is the effective nuclear charge experienced by 3d electron? So in between the nucleus and these 3d electrons which are present, these 1s electron are present, 2s 2p electron are present, 3s 3p electron are present, and also we want to calculate the effective nuclear charge for that d electron, one of the d electrons. The total electron in the d are 10. Total electrons are 10, and we want to calculate the effective nuclear charge experienced by per electron, by one electron. So these remaining 9 electrons which are present in the d will cause something screening effect, will cause something steric hindrance, will cause something restriction, to cause an interaction, to cause an attraction between the nucleus and that d electron. मीन जो ये d का इलेक्ट्रॉन है, जब d के इलेक्ट्रॉन की अट्रैक्शन होगी न्यूक्लियस के साथ, तो उस अट्रैक्शन के बीच में जो रेस्ट्रिक्शन क्रिएट करेंगे, जो रुकावट पैदा करेंगे, वो इलेक्ट्रॉन इस d के भी होंगे. इस d के भी जो रिमेनिंग 9 इलेक्ट्रॉन हैं वो स्क्रीनिंग इफेक्ट क्रिएट करेंगे. इनर वाले और तो करेंगे ही करेंगे, 1s 2p 2s, these all electron will cause the screening effect, and along with these electron, the remaining electron of the 3d will also cause something screening effect. Okay, and what is the value of that screening effect, that we have to learn here. Okay, so that is the point number 2, right? Now the point number third is, now we will discuss about that value, that screening constant value being caused by these inner shell electrons, but that we will discuss in that particular next point. So in next point we will see that the electrons which are present in the same group, same group means, for example, as we talking about that effective nuclear charge experienced by these 3d electrons. So what is the total number of electron in 3d? Total electrons are 10. And we want to calculate the effective nuclear charge of that d electron. D means kept one electron alone. उस एक electron के ऊपर what is the effect of these remaining 9 electrons? Nine electrons. So that is the meaning of the electron in the same group. Electron in the same group. So electron in the same group will cause a screening constant of the value of 0.35, that we have to learn. That value is for the electrons which are present in the same group. देखो अभी तक हमने क्या पढ़ा था कि कोई भी इलेक्ट्रॉन अगर सेम सब शेल में प्रेजेंट है, जैसे 3d10, डी के जो 9 इलेक्ट्रॉन है, हम रीजनिंग टाइप क्वेश्चनों को जब एक्सप्लेन करते हैं तो उसके दौरान हम क्या मान लेते हैं कि ये जो डी के इलेक्ट्रॉन्स हैं वो आपस में एक दूसरे के लिए स्क्रीनिंग का काम नहीं करते। लेकिन स्लेटर रूल के अनुसार डी के रिमेनिंग इलेक्ट्रॉन भी एक दूसरे के लिए स्क्रीनिंग का काम करते हैं। और वो कितना करते हैं, वही हम इस पॉइंट के अंदर डिस्कस कर रहे हैं। सो द इलेक्ट्रॉन्स विच आर प्रेजेंट इन द सेम ग्रुप will cause the screening constant value of 0.35. Okay, so that is the meaning of that point, right? Next is exception here is about the 1s. Means for example, if the question is asked here in that way, कि what is the effective nuclear charge experienced by 1s electron, तो अगर आप इसको देखते हैं तो आपको ये लगता है कि इधर न्यूक्लियस है और पहली शेल ही तो है 1s, तो इलेक्ट्रॉन की जो न्यूक्लियस की डायरेक्ट अट्रैक्शन हो जाएगी 1s इलेक्ट्रॉन के लिए। तो लेकिन यहाँ पे 1s के अंदर 2 इलेक्ट्रॉन हैं, तो हम वांट टू कैलकुलेट द इफेक्टिव न्यूक्लियर चार्ज एक्सपीरियंस बाय एन इलेक्ट्रॉन, एक इलेक्ट्रॉन के द्वारा। तो एक इलेक्ट्रॉन के द्वारा करें तो जो दूसरा इलेक्ट्रॉन है 1s के अंदर, वो इस एक दूसरे इलेक्ट्रॉन के साथ स्क्रीनिंग कर रहा है, उसके अंदर रुकावट पैदा कर रहा है। वो जो न्यूक्लियस के साथ इस एक 1s की इलेक्ट्रॉन की अट्रैक्शन हो जानी चाहिए, उसके अंदर वो स्क्रीनिंग का काम कर रहा है। सो द वैल्यू फॉर दैट इज 0.31। इतनी रुकावट, इतनी क्या है, रुकावट, स्क्रीनिंग कांस्टेंट इतनी कर रहा है। एंड दैट वैल्यू 0.31 इज only when we want to calculate the effective nuclear charge experienced by 1s electron. So when any of the question is asked in such a way that for any of the atom, okay, what is the effective nuclear charge experienced by 1s electron, then you will write the value of screening constant for that 1s electron is 0.30, right? Now the next rule is rule number next. हमने अभी तक ऊपर ये पढ़ा कि सेम ग्रुप की बातें अभी तक देखी कि इलेक्ट्रॉन अगर सेम ग्रुप में है तो कितना स्क्रीनिंग कांस्टेंट क्रिएट करेगा। लेकिन सारे इलेक्ट्रॉन तो सेम ग्रुप में नहीं होते, ऑल द इलेक्ट्रॉन्स आर नॉट प्रेजेंट इन द सेम ग्रुप। फॉर एग्जांपल, इन केस वी आर डिस्कसिंग अबाउट द इफेक्टिव न्यूक्लियर चार्ज एक्सपीरियंस्ड बाय दीज डी इलेक्ट्रॉन्स। तो डी इलेक्ट्रॉन्स के बारे में जब हम बातें कर रहे हैं तो डी के केस में अगर ये जो 9 इलेक्ट्रॉन्स हैं, इनकी वैल्यू का तो हमें पता चल गया कि इनकी स्क्रीनिंग कांस्टेंट कितनी होगी, इनकी वजह से रुकावट कितनी होगी, वो वैल्यू तो कितनी होगी इन द सेम ग्रुप, वो तो हमने देख ली 0.35। व्हाट अबाउट द स्क्रीनिंग कांस्टेंट वैल्यू ऑफ दीज इंटरवेनिंग शेल इलेक्ट्रॉन्स, जो अंदर ग्रुप बने हुए हैं, उनकी वजह से वैल्यू क्या होगी। अब वो अगले पॉइंट में हम आपको बताने जा रहे हैं। तो उसके लिए हमें क्या देखना है, सबसे पहले हम देखेंगे वो वैल्यू कि जब कभी भी कोई ऐसा क्वेश्चन पूछा जाए कि व्हाट इज द इफेक्टिव न्यूक्लियर चार्ज एक्सपीरियंस्ड बाय एनी ऑफ द s इलेक्ट्रॉन और द p इलेक्ट्रॉन, एस और द पी इलेक्ट्रॉन, वो एस चाहे किसी भी शेल का हो, वो पी आपका चाहे किसी भी शेल का हो, फर्स्ट शेल, सेकंड, थर्ड, फोर्थ एंड सो ऑन। तो whenever the question is asked in such a way that what is the effective nuclear charge experienced by the s and the p electron, so if the electrons are present in the same group, for example question is asked about that 3p electron, what is the effective nuclear charge experienced by these 3p electron। जो ये 3p इलेक्ट्रॉन है जिनकी कॉन्ग्रेगेशन हमने लिख दी, जिनकी कॉन्ग्रेगेशन लिखने के बाद जो ये 3p इलेक्ट्रॉन है, इन 3p इलेक्ट्रॉन के द्वारा कितना इफेक्टिव न्यूक्लियर चार्ज एक्सपीरियंस्ड होगा, तो उसके लिए हम पहले क्या करेंगे, हम पहले इस ग्रुप को देखते हैं। इस ग्रुप के अंदर टोटल 8 इलेक्ट्रॉन्स हैं, देयर आर टोटल 8 इलेक्ट्रॉन इन द सेम ग्रुप। तो एक तो 3p का हो गया, बच गए कितने इलेक्ट्रॉन, बच गए रिमेनिंग 7 इलेक्ट्रॉन सेम ग्रुप के हैं। तो जो 7 इलेक्ट्रॉन है सेम ग्रुप के, उनकी वजह से जो स्क्रीनिंग कांस्टेंट होगा, उसकी जो वैल्यू होगी वो तो कितनी होगी, 0.35 इज द वैल्यू ऑफ द स्क्रीनिंग कांस्टेंट बाय दीज 7 इलेक्ट्रॉन्स, 7 extra electrons, 7 remaining electrons of the same group. What about the electrons present just inner to it? Just inner means n-1 means उससे just अंदर वाली जो शेल वाले हैं वो कितने हैं, तो n-1। So these are total 8 electrons and their value will be the 0.85. The screening constant value for the electron, what type of these electrons which are present just inner to it means n-1. So for these 8 electrons the screening constant value will be 0.85. For the remaining electrons, all n-1 and all remaining electrons, for example here the n-2, there is 1s2 electron, the screening constant value will be 1. That rule that I told you just now, that is applicable only for S and P electrons. If the question is asked about the S and P electron, if the question is asked what is the effective nuclear charge experienced by S and P electron, then and only then that point number 4 will be followed, not by D and F electrons. Okay. So if the question is asked what is the effective nuclear charge experienced by S, any of the S or the P electron, you will use the point number 1 means you will form the group. Point number 2 means you will see the particular subshell electron and outer, और जो बाहर के जितने भी इलेक्ट्रॉन है, इलेक्ट्रॉन्स just present outer to that particular subshell in which a particular electron is present, for which we want to calculate the effective nuclear charge. तो जो outer shell के electron है, they will cause no screening effect. That is the point number 2. Next, the point number 3, the electron present in the same group will cause the screening effect value of 0.35. At exception for the 1s, the value is 0.30, right? For the S and P, the inner electrons, if the inner electrons are of n-1, the screening constant value will be 0.85. And next inner, n-2, and more inners all have screening constant value of 1. Now the rule for D and F electrons. D and F electron. For example, we want to calculate the screening, what is the effective nuclear charge experienced by these 3D electrons. So the point number 1 मीन्स फॉर्मेशन ऑफ द ग्रुप, हमने पहले से यहाँ पे ग्रुप बना दिए. पॉइंट नंबर 2 जो हमें ये बताता है कि 3D इलेक्ट्रॉन का इफेक्टिव न्यूक्लियर चार्ज निकालना है, तो इससे बाहर वाली कोई भी शेल हो, फॉर एग्जांपल 4s है, तो उसके जो इलेक्ट्रॉन है वो कोई स्क्रीनिंग का काम नहीं करेंगे. मीन्स आउटर शेल इलेक्ट्रॉन विल कॉज द नो स्क्रीनिंग इफेक्ट, they will have 0 screening constant value. Okay, for the effective during the calculation of effective nuclear charge by these 3D electrons, the rule is applicable. That is the point number 3, that is the electrons which are present in the same group 3D, means these 9 electrons. So value of screening constant for these remaining 9 electrons will be 0.35. Okay, for the remaining electrons which are present just inner to that 3D, means present between the nucleus and the 3D, these all electron, count all these electrons in collective way, is the total electrons are here 3s2 3p6 8 electron, 2s2 2p6 8 electron, and these 2 electrons, means total 8 8 16 to 18. All these inner electrons, the value of screening constant will be 1. There is no bifurcation here like in case of the S and the P, where the electrons n-1 electron have the value 0.85, n-2 and inner have the 1 electron. Here is directly the electron for the D subshell electrons. For the calculation of the effective nuclear charge for any of the D or the F subshell electron, just see the number of electron in the same group. The screening constant for that is 0.35, and all inner electrons, the screening constant value will be 1. So these are the basic rules for the determination of the effective nuclear charge using these rules called as the Slater's rule. So now we will calculate the effective nuclear charge one by one. So first question is calculate the effective nuclear charge experienced by 1s electron in hydrogen atom. The name of the atom is hydrogen atom. So what is the configuration of the hydrogen is 1s1, because atomic number is 1, or all other system which have only 1 electron. For example, in case of helium, the atomic number is 2, but He plus 2. He plus 2 means 1 electron get lost. So the configuration of He plus 2 is 1s1, means like that of the hydrogen, means 1 electron system. All the species whether they are like that of the hydrogen atom, means other ionic species which have only 1 electron, all will have the same answer as I am going to explain here. Okay, so first of all you have to write the electron configuration. After writing the configuration, make the group. Point number 1, as there is only first shell, so there is no further groups, there is only one group, that is the 1s1. Okay, and there is only 1 electron, there is only 1 electron, so the value of screening constant is 0, because there is no other electron. In case of hydrogen in 1s, there is only that 1 electron, no other electron which can cause the screening effect, which can, whose screening constant we want to determine. There is no other electron, so the value of screening constant here in case of the hydrogen atom is 0. If there is something another electron, then the value will be 0.30. That's the exception in point number 3. You can see here for the 1s, the screening constant value is 0.30. But that 0.30 is for another electron. If it is present here, in case of the hydrogen atom, there is no other electron. So no other electron means 0 electron, means we have right here. We have calculated the sigma value, means 0 multiplied by 3, 0.30 means 0. So what is the effective nuclear charge experienced by the 1s electron? Means the actual charge, that is the nuclear charge, that is the actual charge is 1 minus screening constant. Screening constant value is also 0. So 1 minus 0 is 1. Means the effective nuclear charge and the nuclear charge value is same here for the hydrogen. For that 1s electron in case of hydrogen. Okay, so the same is the case for the all one electron system. For all one electron system, the value of nuclear charge is equal to the effective nuclear charge. Okay. Now we will take another example. What is the effective nuclear charge experienced by 1s electron in helium? That is a 2 electron system. In all 2 electron system, the answer will be the same. So for 1s electron in helium, we first of all write the electron conjugation. The conjugation is 1s2. Now make the group. There is only first shell, so only one group. Now you can see in case of the helium here, there are 2 electrons in 1s, and we want to calculate the effective nuclear charge experienced by 1s electron. So for one electron, the other electron which is present in the same 1s orbital, that will cause something screening constant. So what is the screening constant value for 1s here? That is the 0.30. Okay. So 1 multiplied by 0.30 is equal to 0.30. आपको एक चीज का ध्यान रखना है, जब कभी भी ये कहा जाए कि एक इलेक्ट्रॉन का इफेक्टिव न्यूक्लियर चार्ज निकालें, तो उस पार्टिकुलर ग्रुप के अंदर उस एक इलेक्ट्रॉन को छोड़कर बचे हुए इलेक्ट्रॉनों को हमें काउंट करना है और उसको मल्टीप्लाई करना है स्क्रीनिंग कांस्टेंट की वैल्यू से। जैसे हमने बताया कि 1s के लिए जो स्क्रीनिंग कांस्टेंट की जो वैल्यू होती है वो 0.30 होती है, और उस एक इलेक्ट्रॉन का जिसका हमें इफेक्टिव न्यूक्लियर चार्ज निकालना है, उस इफेक्टिव न्यूक्लियर चार्ज को छोड़कर बचे हुए इलेक्ट्रॉन एक ही हैं, इसलिए हमने एक से मल्टीप्लाई किया 0.30 को। ओके, सो वी ऑलवेज हैव टू मल्टीप्लाई द नंबर ऑफ इलेक्ट्रॉन by subtracting the one particular electron. So the screening constant value here is 0.30. So what is the effective nuclear charge experienced by 1s electron? Means the nuclear charge. Nuclear charge means the atomic number of the helium. The atomic number of the helium, nuclear charge, the actual nuclear charge is the 2 minus screening constant. Screening constant is 0.30. So the effective nuclear charge experienced by 1s electron in helium is 1.70 is the answer. Okay, now we will take the next example. Calculate the screening constant value for 1s electron in lithium, or in other way we can say that calculate the effective nuclear charge experienced by 1s electron in lithium. हम बात कर रहे हैं कि 1s इलेक्ट्रॉन कितना एक्सपीरियंस करेगा इफेक्टिव न्यूक्लियर चार्ज। तो जो कॉन्फ़िगरेशन हम लिखेंगे लिथियम की 1s2 1s2 2s1 2p0 means the all the electrons, all the orbitals, all the shell or the subshell which are present just outer to the first 1s will have zero screening constant value, will have zero screening effect. तो मीन्स 1s से बाहर जो भी आपके प्रेजेंट हैं ये जो इलेक्ट्रॉन 2s1 में 1 इलेक्ट्रॉन, इसके ये कोई भी स्क्रीनिंग क्रिएट नहीं करेगा 1s इलेक्ट्रॉन के लिए। हमें कैलकुलेट करना है यहाँ पे इफेक्टिव न्यूक्लियर चार्ज एक्सपीरियंस्ड बाय 1s इलेक्ट्रॉन इन लिथियम। सो द फॉर 1s इलेक्ट्रॉन, तो इन केस ऑफ 1s देयर आर 2 इलेक्ट्रॉन, तो इसीलिए 1s के अंदर एक इलेक्ट्रॉन का हमें इफेक्टिव न्यूक्लियर चार्ज निकालना है, तो उस एक को छोड़ के जो बचा हुआ एक इलेक्ट्रॉन है सिर्फ वही स्क्रीनिंग कांस्टेंट क्रिएट करेगा, वही स्क्रीनिंग इफेक्ट क्रिएट करेगा। तो वो जो एक इलेक्ट्रॉन हम यहाँ पे 1 से मल्टीप्लाई करेंगे, यहाँ पे हमने गलती से 0 लिख दिया, आप यहाँ पे 1 लिख लेंगे, तो 1 मल्टीप्लाइड बाय 0.30 इज इक्वल टू 0.30। सो द इफेक्टिव न्यूक्लियर चार्ज एक्सपीरियंस्ड बाय दैट 1s इलेक्ट्रॉन इन लिथियम इज, एज द न्यूक्लियर चार्ज इज एक्चुअल न्यूक्लियर चार्ज इन लिथियम इज 3 बिकॉज एटॉमिक नंबर इज 3, तो 3 माइनस स्क्रीनिंग कांस्टेंट Is answer is 2.70. That is the effective nuclear charge experienced by 1s electron. Okay. Next question. What is the effective nuclear charge experienced by 2s electron in lithium? In the similar way, जो 2s है आपका, उसका जो एक ही इलेक्ट्रॉन है और तो कोई इलेक्ट्रॉन है नहीं, तो इस पर्टिकुलर इलेक्ट्रॉन के लिए जो स्क्रीनिंग क्रिएट करेगा वो जस्ट इनर इलेक्ट्रॉन ही क्रिएट करेंगे, वो 1s वाले इलेक्ट्रॉन है. सो दीज इनर 1s इलेक्ट्रॉन विल कॉज द स्क्रीनिंग कांस्टेंट फॉर दैट 2s इलेक्ट्रॉन. सो हाउ कैन वी कैलकुलेट द स्क्रीनिंग कांस्टेंट? जो आपके यहाँ पे 2s के अंदर जो इलेक्ट्रॉन है, तो उसके लिए वैल्यू कितनी होनी चाहिए? 0.35. लेकिन 2s अकेला है और कोई इलेक्ट्रॉन है नहीं, कोई और नहीं, तो हमने 0 लिख दिया. मल्टीप्लाइड बाय अगर कोई होता तो स्क्रीनिंग कांस्टेंट वो कितनी क्रिएट करता? वो करता 0.35. अब तो कोई और इलेक्ट्रॉन है नहीं, तो इसलिए इसको चाहे हम लिखे ना लिखे इससे कोई फर्क नहीं पड़ता. सिर्फ आपको समझाने के लिए मैंने यहाँ पे लिखा कि y0 y 0.35. सो द नेक्स्ट इनर वन 1s2. तो जस्ट इनर के लिए क्या हमने लिखा था? क्योंकि आपका जो ग्रुप है ये s और p के लिए है, और s और p के ग्रुप के लिए जो जस्ट इनर इलेक्ट्रॉन्स होते हैं उस पार्टिकुलर ग्रुप से जस्ट इनर, क्योंकि हम इफेक्टिव न्यूक्लियर चार्ज 2s के लिए निकाल रहे हैं, तो 2s इस ग्रुप में प्रेजेंट है. इस ग्रुप से जो जस्ट इनर वाला ग्रुप होगा जिसे n-1 कहेंगे, उसके लिए स्क्रीनिंग कांस्टेंट की वैल्यू क्या है? 0.85. और उसमें इलेक्ट्रॉन कितने हैं? 1s2 इलेक्ट्रॉन है, तो 2 इलेक्ट्रॉन्स हैं. स्क्रीनिंग कांस्टेंट की वैल्यू 0.85, तो टोटल आंसर कितना आ गया? 1.70. अब हम क्या करेंगे इफेक्टिव न्यूक्लियर चार्ज कैलकुलेट करने के लिए? जो एक्चुअल न्यूक्लियर चार्ज है लिथियम का एटॉमिक नंबर 3 है, तो 3 माइनस 1.70. सो द आंसर इज 1.30. सो इन दैट वे वी कैन कैलकुलेट द इफेक्टिव न्यूक्लियर चार्ज experienced by the 2s electron in case of the lithium. Next example is calculate the effective nuclear charge experienced by 1s electron in neon. So first of all, write the electronic configuration of the neon: 1s2 2s2 2p6. As we have to calculate the effective nuclear charge experienced by 1s electron, so the effect due to these outer shell electrons will be 0. Means if screening effect is 0, screening constant value is 0. So what we will observe, simply we will concentrate only on the 1s. सो द स्क्रीनिंग कांस्टेंट वैल्यू विल बी, क्योंकि 1s के लिए हमें निकालना है, 1s में 2 इलेक्ट्रॉन थे, के लिए निकालना है, तो रिमेनिंग इलेक्ट्रॉन इज ओनली 1. सो वी राइट हियर 1 एंड द वैल्यू ऑफ स्क्रीनिंग कांस्टेंट इज 0.30 फॉर दैट 1s इलेक्ट्रॉन. ओके, सो द 1 मल्टीप्लाइड बाय 0.30 इज इक्वल टू 0.30. सो द आंसर इज 10 is the atomic number of the neon, that is the actual nuclear charge. 10 minus that screening constant value 0.30 is equal to 9.70 is the answer. The next question is calculate the effective nuclear charge experienced by 2s electron in the neon. So these 2s electron, that is the complete group. आपको ये ध्यान रखना है 2s इलेक्ट्रॉन के लिए भले ही हम निकाल रहे हों, लेकिन हम कंसीडर करेंगे 2s और 2p को एक ही ग्रुप के अंदर. 2s इलेक्ट्रॉन का इफेक्टिव न्यूक्लियर चार्ज निकालना है, तो इस ग्रुप में जो रिमेनिंग इलेक्ट्रॉन है वो कितने और हो गए? टोटल इलेक्ट्रॉन थे 6 + 2 8. एक इलेक्ट्रॉन का हमें निकालना है 2s इलेक्ट्रॉन का, तो बचे हुए इलेक्ट्रॉन हो गए 7. तो इन 7 इलेक्ट्रॉन का स्क्रीनिंग कांस्टेंट हमें कैलकुलेट करना है, क्योंकि ये स्क्रीनिंग क्रिएट करेंगे. तो जो सेम ग्रुप के अंदर s और p के सेम ग्रुप के अंदर जो इलेक्ट्रॉन प्रेजेंट होते हैं, जो 7 इलेक्ट्रॉन है, वो कितना स्क्रीनिंग कांस्टेंट क्रिएट करेंगे? उसके लिए वैल्यू हमने कितनी दे रखी थी? इन द सेम ग्रुप हो तो 0.35. तो 7 मल्टीप्लाइड बाय हम 0. कितना कर देंगे? 35. जो नेक्स्ट इनर है n-1 के लिए बोलो कितनी होगी वैल्यू? दैट इज 0.85. तो इन 2 इलेक्ट्रॉन के लिए 0.85 होगी. एक चीज और, कुछ बच्चे मेरे से ये पूछ रहे हैं कि सर ये बताइए, आपने यहाँ पे लिखा कि 1s के लिए 0.30 होगी, तो अभी आपने ऐसा क्यों कहा कि जो ये इनर शेल इलेक्ट्रॉन है n-1 वो 1s के ही तो हैं, तो उनके लिए आपने वैल्यू 0.85 क्यों कही? मैं आपको फिर से याद दिला दूं, ये 1s के लिए 0.30 इसलिए कहा जा रहा है कि अगर क्वेश्चन कोई ऐसा आए कि कैलकुलेट द इफेक्टिव न्यूक्लियर चार्ज एक्सपीरियंस्ड बाय 1s इलेक्ट्रॉन, ऐसा पूछा जाए, तो उस केस में ही आप जो वैल्यू लिखेंगे स्क्रीनिंग कांस्टेंट की 1s के लिए, वो 0.30 लिखेंगे. सिर्फ तभी जब क्वेश्चन कैसा आए, कैलकुलेट द इफेक्टिव न्यूक्लियर चार्ज एक्सपीरियंस्ड बाय 1s इलेक्ट्रॉन इन एनी ऑफ द एटम. ओके, so that's the way. So now we will calculate the screening constant value. You can see in the same group, as we have to calculate the effective nuclear charge for the 2s, means screening constant for 2s. तो आपके जो ये ग्रुप है 2s2p वाला जो ग्रुप, इसमें कितने इलेक्ट्रॉन्स हो गए? रिमेनिंग इलेक्ट्रॉन 7, क्योंकि एक का तो हमें कैलकुलेट करना है। तो 7 को बोलो हमने किससे मल्टीप्लाई किया? 0.35 से, बिकॉज द रिमेनिंग 7 इलेक्ट्रॉन्स आर ऑफ द सेम ग्रुप। फॉर सेम ग्रुप द रूल इज 0.35। ओके, तो 7 मल्टीप्लाइड बाय 0.35। और क्योंकि हम 2s के लिए कैलकुलेट कर रहे हैं, तो s और p इलेक्ट्रॉन के लिए जब हम कैलकुलेट करें, उसमें जो जस्ट इनर ग्रुप होता है n-1, उसके लिए वैल्यू क्या होती है? 0.85। तो हमने जो ये दो इलेक्ट्रॉन थे इनर ग्रुप के अंदर, तो 2 मल्टीप्लाइड बाय 0.85, और आपने कैलकुलेट किया और आपका आंसर आया 4.15। अब इसको हम माइनस कर देंगे, जो एक्चुअल चार्ज है नियोन का, जो इसका एटॉमिक नंबर है 10 माइनस 4.15, आंसर इज 5.85। सो द इफेक्टिव न्यूक्लियर चार्ज एक्सपीरियंस्ड बाय 2s electron in case of the neon is 5.85. Okay, now we'll take the next example. If we have to calculate 2p electron, the answer will be same like that of the 2s, because 2s and 2p collectively form the same group. ये दोनों एक ही ग्रुप बनाते हैं, तो इसीलिए जो आपका 2p के लिए भी निकालना पड़े, तो रिमेनिंग जो इलेक्ट्रॉन्स होंगे इस सेम ग्रुप के अंदर वो 7 होंगे। तो 7 मल्टीप्लाइड बाय सेम ग्रुप के लिए 0.35 होता है, इनर ग्रुप के लिए 0.85 होता है। इनर ग्रुप के अंदर दो इलेक्ट्रॉन है, तो 2 मल्टीप्लाइड बाय 0.85, आपका आंसर 4.15। ये स्क्रीनिंग कांस्टेंट की वैल्यू आ गई। और जब इसको माइनस करेंगे हम इफेक्टिव एक्चुअल चार्ज के अंदर से, एक्चुअल न्यूक्लियर चार्ज के अंदर से, तो 10 माइनस 4.15 आंसर आ जाएगा 5.85। ओके, तो नेक्स्ट एग्जांपल इज अबाउट द सल्फर। Calculate the effective nuclear charge experienced by the sulfur for the 1s electron in the sulfur. Write the complete electronic configuration of the sulfur: 1s2, 2s2, 2p6, 3s2, 3p4. As we want to calculate the effective nuclear charge experienced by that 1s electron in sulfur, so these all electrons which are present just outer to that 1s will cause no screening effect, which will cause no screening constant. We have no need to calculate the screening constant for these one, because they causes no steric hindrance for these 1s electron for their attraction towards the nucleus. Okay, so the value is, जैसे कि मैंने आपको पहले कहा था, जब कभी ऐसा क्वेश्चन पूछा जाए कैलकुलेट द इफेक्टिव न्यूक्लियर चार्ज फॉर द 1s इलेक्ट्रॉन, अब वही पूछा गया, तो उस वक्त आपके 1s में दो ही इलेक्ट्रॉन हैं, एक का निकालना है, दूसरे के लिए जो स्क्रीनिंग कांस्टेंट की वैल्यू है, जो स्पेशल केस हमने लिखा था फॉर 1s 0.30, अब देखो हमने लिखा ना यहाँ पे, तो 1 मल्टीप्लाइड बाय 0.30, तो इसीलिए जो आंसर आ जाएगा, क्योंकि 1s इलेक्ट्रॉन के लिए निकाला, सल्फर का एटॉमिक नंबर 16 माइनस 0.30, सो द आंसर इज 15.70। दैट इज द इफेक्टिव न्यूक्लियर चार्ज एक्सपीरियंस्ड बाय 1s इलेक्ट्रॉन इन सल्फर। नाउ व्हाट अबाउट द 2s और द 2p, क्योंकि दोनों एक ही ग्रुप के अंदर हैं। अब चाहे मैं क्वेश्चन आपसे ये यहाँ पे 2p की बजाय 2s लिख के पूछ लूं या 2p, आंसर आपका सेम रहेगा, बिकॉज द 2s एंड 2p फॉर्म द सेम ग्रुप, they are present in the same group. So the question is calculate the effective nuclear charge experienced by 2p electron in sulfur atom. तो in 2p, in that particular 2s2p group there are total 8 electrons, और एक इलेक्ट्रॉन का हमें इफेक्टिव न्यूक्लियर चार्ज निकालना है, तो एक को छोड़ के बचे हुए जो इलेक्ट्रॉन हो गए यहाँ पे 2s2p में, तो 8 माइनस तो 7 हो गए, 7 इलेक्ट्रॉन्स हो गए। तो सेम ग्रुप के अंदर कितना होगा स्क्रीनिंग कांस्टेंट की वैल्यू? दैट इज द 0.35 फॉर द सेम ग्रुप, राइट? So what we have written here, 7 multiplied by 0.35 for just inner to it n-1, because we are here calculating the effective nuclear charge for the 2p electron, और 2p के लिए मीन्स s और p के लिए रूल क्या है, हम n-1 भी देखेंगे, n-2 भी। तो यहाँ पे n-1 हमने देखा, क्योंकि n-1 ही है, दो इलेक्ट्रॉन है, तो 2 मल्टीप्लाइड बाय वैल्यू कितनी होगी n-1 की? 0.85। सो द आंसर हियर इज 4.15 for the screening constant. Now subtract that screening constant from the actual charge of the sulfur. We have wrongly written here the 10. Just write the 16 here. यहाँ पे आप 16 लिखेंगे। क्या लिखेंगे आप यहाँ पे? 16। क्या इसको आप करेक्ट करें? We have made the correction here. We have just write here the 16. So as the atomic number of the sulfur is 16, actual nuclear charge is 16, so subtract the screening constant value, that is the 4.15, so the answer is 11.85। आपको क्या ध्यान रखना है, जो भी मैंने यहाँ पे प्लस माइनस मल्टीप्लाई कुछ भी जो कर रखा, आप उसको अपने लेवल के ऊपर जरूर क्रॉस चेक करेंगे। हो सकता है मेरे कैलकुलेशन के दौरान कोई गलती रह जाए, जैसे मैंने यहाँ पे अभी 10 लिख दिया था सल्फर का एटॉमिक नंबर, तो ऐसे मान लीजिए कोई मिस टाइपिंग हो जाए, मिस प्रिंटिंग हो जाए, तो आप उसको अपने लेवल के ऊपर करेक्ट करते रहेंगे। तो आप इस चीज का जरूर ध्यान रखें। ओके, सो द नेक्स्ट क्वेश्चन इज Now we will calculate the effective nuclear charge experienced by the 3p electron in case of the sulfur. So for the 3p, there is no other outer shell electrons. So all electrons are present inner to it. So first of all, write down the electron configuration for the sulfur: 1s2, 2s2, 2p6, 3s2, 3p4, and make the group for 1s one group, 2s 2p another group, 3s 3p another group. So in the last group, that is the 3p group, for which we want to calculate the effective nuclear charge, there are total 6 electron. Out of these, the 5 electron will cause the screening in the same group. So the screening in the same group, the value is 0.35. You can see here the 5 multiplied by 0.35. Okay. For n-1, that is electrons are 2 plus 6, that is the 8 electron. N-1 value is 0.8 screening constant. You can see here. So 8 multiplied by 0.85. For n-2, that is the 1s here. So total electrons are 2 multiplied by 1, because the screening constant value is 1 for this n2 group, right? So the answer of the screening constant comes out to be 10.55. So now the actual charge is 16 for the sulfur, because atomic number of sulfur is 16, minus the value of screening constant 10.55. So the answer is 5. The answer is 5.45 is the answer. Okay. So that is the effective nuclear charge experienced by the 3p electron. The next question is for the d block element. What is the effective nuclear charge experienced by these 3d electrons in case of the zinc atom? First of all, write down the electron configuration. The configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s2, right? Now make the group. The first group is 1s, second one is 2s and 2p group, next one is 3s 3p group, next one is 3d group, and last one is the 4s group. As we have to calculate the effective nuclear charge experienced by these 3d electron, and the electrons which are just present outer to the 3d, that is the 4s electron, this 4s electron will cause no screening effect, so we have to cut it. देखो मैंने यहाँ पे इसके ऊपर कट लगा दिया है, जस्ट ताकि हमारे puzzling create ना हो. तो अब हम क्या करेंगे? Now the electron which are present in the same group, in the same d group, the total electrons are 10, but the electron, except that one electron to which we want to calculate the effective nuclear charge, that is the 9 electron. So the 9 electron multiplied by 0.35 for the same group, whether the group is of S, P, D or F, for the same group the value is always remains same, that is the 0.35. So 9 multiplied by 0.35. For these two electrons, the screening constant value is 0, because these electrons, that particular 4s subshell is present outer to the 3d, so the 0 value of screening constant, they cause no screening effect. Okay, and there is no need to write here. मैंने सिर्फ आपको समझाने के लिए यहाँ पे लिखा है. For the D, when we are calculating the effective nuclear charge experienced by the 3D for the D electron, then all other inner electron will be sum up collectively. So the inner electrons are the 3s 3p group, total 8 electrons, 2s 2p, total 8 electron, 8 8 16, 1s 2, 8 8 16 to 18, 18 multiplied by 1, because all inner electrons will cause the screening constant value of 1 for the D and F electron. That is the rule number 5. Okay, so the answer comes out to be 21.15. That's the value of screening constant. Now the effective nuclear charge experienced by 3D electron is 30, that the atomic number of the zinc, minus screening constant value is 21.15. The answer comes out to be 8.85. Okay, that's the way how can we calculate the effective nuclear charge experienced by any of the electron. The next question is calculate the effective nuclear charge experienced by the 4s electron in the zinc atom. Write the configuration in the same way. Now you can see here the 4s is the outermost shell. No shell is present after that. No electron is present outside to that particular 4s electrons. So the group is the 4s group, the outermost group. In that same group, there is only 2 electrons, one to whom we want to calculate the effective nuclear charge. So the remaining electron is only 1 in the same group. So for the S, for any of the group, for any of the electron present in the same group, the value is 0.35. So we have written here 0.35 multiplied by 1. That one electron in 4s. Okay, so for n-1 group, n-1, their next group is 3d here. So the total electrons are 10 here. So 10 multiplied by 0.85, all other inner electron n minus 2 and the inner one. So total are the 18 electrons, 6 plus 2, 8, 6 plus 2, 8, and 2, 8, 16 to 18, 18 multiplied by 1. So the answer comes out to be 26.85, the screening constant value. So the effective nuclear charge experienced by these 4s electrons will be the actual nuclear charge, that is a 30, that is the atomic number of the zinc, minus the screening constant value, that is a 26.85. So the answer comes out to be 3.15. That is the effective nuclear charge experienced by the 4s electron in zinc atom. Clear? So that is all about the that is all about that topic, that is the effective nuclear charge. So now we will discuss about the penetration power. That is another important topic after the screening constant, that next factor which generally been used during the discussion of the topic, during the discussion on different topics, the size topic, the ionization energy topic, the electron affinity topic, and so on. In different topic, that term is very important. What is mean by that penetration power? Penetrate means वहां तक पहुंचने की पावर, पहुंचने की पावर, कहां तक पहुंचने की पावर, कोई इलेक्ट्रॉन कहां पे पहुंचना चाहता है, वो किसी चीज की तरफ अट्रैक्ट होना चाहता है, किसकी तरफ अट्रैक्ट होना चाहता है, न्यूक्लियस की तरफ अट्रैक्ट होना चाहता है। तो किसी भी, वेदर द इलेक्ट्रॉन इज प्रेजेंट इन द एस सब शेल और द पी और द डी और द एफ सब शेल, वेदर कहीं पर भी कोई भी इलेक्ट्रॉन प्रेजेंट हो, लेकिन वो जो भी इलेक्ट्रॉन है, वेदर इट इज प्रेजेंट इन एसपीडी और द एफ, दैट पर्टिकुलर इलेक्ट्रॉन बीइंग अट्रैक्टेड टुवर्ड्स द न्यूक्लियस, और जो उसकी इलेक्ट्रॉन, उस पर्टिकुलर इलेक्ट्रॉन की न्यूक्लियस की तरफ अट्रैक्ट हो जाने की जो भी है पावर, वो उसकी पेनिट्रेशन पावर कहलाती है। क्या कहलाती है? उसकी penetration power. So means the extent to which a particular orbital or their electron being attracted towards the nucleus is called their penetration power, is called their penetration power. So the extent to which a particular orbital is attracted by the nucleus is called penetration power, is called penetration power. जो penetration जो power होती है, उसके बीच में आपके, मैंने अभी आपको बताया, वो सभी की अलग अलग होती है, एस की अलग, पी की अलग, डी की अलग, एफ की अलग। तो जो ऑर्डर है पेनिट्रेशन पावर का, वो एस इज ग्रेटर देन, पी इज ग्रेटर देन, डी इज ग्रेटर देन एफ है। ऐसा क्यों? बिकॉज एस इज स्फेरिकल इन शेप and is more nearer to the nucleus. Because of that reason, S penetration power of S is much more greater than that of the P, D and the F subshell. Okay, so the penetration power of S orbital or the subshell is greater than that of the P, D or the F orbitals. So that is about the penetration power. You have to learn that particular point. Okay, so that's all about our today's topics, that is the nuclear charge. What is nuclear charge? What is effective nuclear charge? What is screening constant? What are the factors which affect the screening constant? And what are the Slater's rule by using which you can calculate the effective nuclear charge? And the last point is here the penetration power. Okay, what do you mean by the term penetration power? And what is the penetration power order of these different sp and the d subshell orbitals? So that all about the today's session or the lecture. Hope you well enjoyed in that particular session. You have learned, I have given to my maximum. So if there is something limitation you want to ask any of them, just write in the comment box. I will give the answer to you. So okay, thank you for keeping patience, for keeping patience, and और इसी टाइप से आप इन सारी बातों को ऐसे ही सुनते रहें और एंजॉय करते रहें। थैंक यू।